So we are picking up in 5.1 part 1, and we are now on the back of that page. Now, if you recall, you have those identities on the front side, so you are going to have to keep the identities familiar, okay? So we have all those identities we talked about and introduced yesterday. But on the back side, what we're going to spend the rest of this lesson working on is practicing simplifying expressions. As you kind of glance at these, you'll notice none of them are small, easy peasy expressions, okay? However, with the help of our identities, we're going to be able to simplify a lot of these to just one trig function, okay? So it's going to take some maneuvering, some manipulating, and the use of our identities. Now, I'm not going to call these steps up top because you don't necessarily follow them in order, but there are 5 suggestions of steps you can consider. Okay? We can create common denominators to combine fractions. So if you have multiple fractions or expressions, you can work to combine them. Okay? We can separate numerators by dividing each piece by a denominator. If you see something that would be better, separate it into 2 fractions. And the 3 that are really important. Number 3, we're going to use our algebra steps and factor or FOIL. Okay, where you can factor a GCF out maybe, or use a product and sum factoring. Or we could FOIL some things together. 4, look for the Pythagorean identities. If there is a Pythagorean identity or a variation that can be substituted out, like something equals something, we can replace it. And then the final one is an option that sometimes is helpful, is change all trig functions to sine and cosine within a problem. And if you think about it, they can all be changed. Okay, between reciprocals and quotient identities, everything has its basis in sine and cosine. Sine or cosine. And or cosine. How's that? Okay, so we're going to work on those things. So, example A. Sine cubed x plus sine x cosine squared x. We're looking for an idea. Okay. Now, I would say 1 and 2 are out because this is just 2 terms being added. There's no fractions to talk about.
I figured 5's out.
5 is out because everything's already sine and cosine. So at that point, we're factoring or foiling or looking for Pythagorean identities or something not on the list. Any thoughts?
Try to factor FOIL this.
Okay. One type of factoring that we talk about is GCF. Is there something in common here?
Sine x.
Do both terms have a sine? Sine of x. They do, yes? Okay. Both these terms, the first term has sine cubed x, so it has, sine cubed, so 3 of them. This other one has a sine x, yes? So the first step we're going to talk about, and I'm kind of writing steps out today just to kind of give you ideas of what we're doing, is we're going to factor a GCF out. So both terms have a sine in common, yes? So think GCF. What do? We put the GCF out front, and then what remains when we divide that GCF? So what is sine cubed x divided by sine of x?
Sine squared x.
Does that make sense? It's a lot like saying what is x cubed divided by x, right? If I had asked you what is x cubed divided by x, that would be x squared, right? So what is sine cubed divided by sine x? That is sine squared x. Plus, what is sine x cosine squared x when you divide out sine x?
Cosine squared x.
The sine x will cancel, and you'll be left with cosine squared x. Pause for a moment. Are we okay with that? I mean, as okay as it gets, being this is our first example. Okay? Yes, no, I don't know. Okay. Now, you're not usually done in one step. We factored, so that kind of takes out the factor or FOIL part. Do you see anything? Is there a Pythagorean identity there?
Yeah.
And this is where we have to flip back and forth, right? Those Pythagorean identities are going to be useful. If you go to your Pythagorean identities, what is that first Pythagorean identity?
Sine squared theta plus cosine squared theta equals 1.
Okay, so the idea of sine squared plus cosine squared equals 1. Now, our identities on the front page say theta. This says x. Realize it's just a different variable.
So therefore,
X is a variable, theta is a variable, y is a variable. You know, they're all variables.
therefore your answer is just sine of x.
Yes? Okay. Are we okay that sine squared x plus cosine squared x is just going to be 1? So then you have sine x times 1. And sine x times 1 is indeed sine x. So thus my statement earlier that we get a lot of answers that are just single trig functions. Sine x is a single trig function. Now, I'm writing kind of big. This is probably going to get me in trouble. But if you want, write yourself a note. How did we get from this step to this step? We used a Pythagorean identity. Okay, so feel free to write yourself some notes like, what did we do there? And that was a Pythagorean identity. Okay? Okay. Did we at least kind of see that when it was pointed out to us? Okay. And the step of what's the hard part? Seeing it on your own, right? I think you guys can follow it. That's what takes practice, is being able to see the stuff on your own. Okay, let's look at B. Secant x plus 1 times secant x minus 1 over sine squared x.
Number 2. Separate the numerator by dividing each piece by the domain. Okay,
I was just trying to think if we could make that work. And because here's the other thing. Is there just one way to do some of these? Not necessarily. So, you know, sometimes you have to give me a moment. I don't think we could separate that. Huh? The only problem with changing secants to cosine at this point is when I change a secant to a cosine, it's going to become a fraction. Like secant is 1 over cosine, then we're going to have fractions within fractions, which gets ugly. What about 2 parentheses? What do those 2 parentheses make you think? Could we FOIL them? Could we take this numerator and FOIL?
He doesn't want to.
Whether you want to or not, it's the easiest way that comes to my brain to do this. Okay? And this is definitely one of those things. There's not one right way to do this. Okay? Now, when you FOIL, you guys know how to FOIL, right?
No.
First, secant x times secant x. What do you think secant x times secant x is?
Secant x squared. Or secant squared x.
Okay, I'm going to write it as secant squared x. Okay. Now, what about when you multiply the outside? Secant x times negative 1.
So it'd be negative minus secant x.
Minus secant x. What about when you multiply the insides?
Plus secant x.
Secant x times positive 1 is plus secant x. What are you noticing at this moment?
Get rid of each other.
A minus secant x and a plus secant x. Are those going to cancel out? Yeah. So your outsides and your insides are going to cancel out, and then you can jump to the last. Positive 1 times negative 1? Minus 1. All still over sine squared x. Okay? Now, folks, recognize on top, we have multiplied conjugates before. That's what those are on top, right? When they're the same pieces, opposite signs in the middle. That's your clue that, oh yeah, the outsides and insides are going to cancel. Okay. Let's keep working with that top for a moment. We have secant squared x minus 1. You should indeed be flipping and looking at your identities.
This is equal to tan squared theta secant squared theta with minus 1 would be equal to tan squared.
And why is that?
Because the original equation is 1 plus tan squared theta equals secant, so if you subtract the 1, it would become secant minus 1 equals tan.
Do you guys see the...
I get tired of saying the square of theta. So
I get it. It's a lot to say. Okay, so do you guys see the Pythagorean identity? 1 plus tangent squared x equals secant squared x. Do you see that Pythagorean identity? Yes? And here's what I'm going to tell you, okay? When you see squared functions added or subtracted with other squared functions or 1, check your Pythagorean identity. You'll hear me say that lots as we go through this unit, okay? Here is a squared function added or subtracted with 1. There is a good chance, not guaranteed, that it's going to equal a Pythagorean identity. Now, secant squared x minus 1, can I manipulate this? Sure can, subtract the 1 over. And so then I know that tangent squared x is equal to secant squared x minus 1. So what are we saying here? Every place we see a secant squared x minus 1, I can replace it with tan squared x. Okay? So let's do that. Secant squared x minus 1 becomes tan squared x, still over sine squared x. If you want to write yourself a note, how did we get there? We used a Pythagorean identity. Okay. We're still going. Options include looking back at our list of 5 suggestions to see if anything makes sense there, and looking at our identities to see if anything helps there. And I know I vetoed earlier in this problem having fractions within fractions. And my reasoning up here earlier is it would have been 1 over cosine plus 1, 1 over cosine minus 1. That just would get kind of ugly.
You can make it sine over cosine over sine.
Okay. So talking about basically the idea of changing everything to sine and cosine. Okay. What do we know about tangent?
Equal sine over cosine.
According to our quotient identity, tangent is sine over cosine. So that means that tangent squared is sine squared over cosine squared. Now, Logan read it off as sine squared over cosine squared over sine squared, which you can think of it that way. I'm also going to show writing it horizontally because I think that's going to make more sense to you on this problem. And I'm going to do that right before I switch to the fraction. So I'm just going to do a rewrite here. that tan squared x, this is tan squared x divided by sine squared x. True?
Yeah.
The suggestion was to change using the quotient identity tangent to sine over cosine. Or in this case, since it's tangent squared, it's going to be sine squared x over cosine squared x divided by sine squared x. Now, are you with me on what I did? This was the quotient identity.
So you're officially multiplying by 1 over sine squared x. So sine squared x we cancel out. It's going to be cosine squared x. Or no, it would be 1.
So I wrote it like this so you could see, if we think of sine squared x over 1, this is a fraction divided by a fraction, right? How do we do a fraction divided by a fraction? Well, the middle school voice in your head says keep, change, flip, right? So we're going to keep sine squared x over cosine squared x. I'm going to change division to multiplication, and I'm going to flip, and it's going to be 1 over sine squared x. Now that you have those two fractions, this is where cross-canceling is good, yes?
So
Because sine squared x can cancel with sine squared x. If you multiply across, you have 1 over cosine squared x. Now, I'm going to tell you, the answer key is never going to, I maybe shouldn't use the word never. Pretty much always, almost always, we'll go one more step. It won't leave like 1 over a trig function.
So would it be secant squared
Yeah.
x?
A cosine in the denominator, well, cosine is the reciprocal of secant. So a cosine in the denominator is a secant squared. So this is secant squared x. Okay? And that, I guess I didn't write my last couple of steps out. Well, it's just the one here. And that was the fact that we used a reciprocal identity. Okay? Okay. So I'm not against doing fractions within fractions. There's just a time and a place. And to start off wasn't the right time and place. Once you get to where it's just one thing divided by one thing, that's not bad for fractions within fractions. Okay? It all just depends on the scenario and what other options exist. And again, I'm not going to say this is the only set of steps to solve this problem. Okay? Ready to try C? Okay. Cosine of x over 1 minus sine x over cosine x.
Create common denominator.
Okay. We have two fractions being subtracted, don't we? Two fractions being subtracted. It would be nice to put it, more often than not, it's nice to put two fractions into one fraction to work with. So, yes, I am going to suggest a common denominator. What would be my common denominator? Think about it this way. If we have, say, 1/2 plus 1/3, what's a common denominator if you have 1/2 plus 1/3?
Then multiply together.
2 times 3, which is 6, yes? Okay, guys? If there's nothing in common, your common denominator is just multiplying your denominators. That's what I'm suggesting here. 1 minus sine x and cosine x. I didn't say this was pretty. Okay? I'm never going to say any of these are pretty. You get some short problems, you get some longer problems. That's going to be my common denominator. Now, with that in mind, okay? So, that means both fractions are going to have the denominator of cosine x times 1 minus sine x. Minus, my second fraction is also going to have cosine x times 1 minus sine x. Okay? Now, with that in mind, my question to you. My first fraction has a 1 minus sine x. What piece of the denominator am I missing? We're missing the what? If we have the 1 minus sine x, we're missing the cosine x?
Yeah.
Right? So on the first fraction, to get that common denominator, I have to multiply the denominator by cosine x. Well, in a fraction, what you do on bottom, you do on top, yes? So that means we're going to multiply the top by cosine x as well. Okay, on top, what is cosine x times cosine x? Okay. Officially, cosine squared x. We're not putting the squared after the x's, right? Because if you are, you have to use parentheses there around the whole thing. Okay, second fraction has a cosine x in the denominator. What piece of the denominator am I missing? I'm missing the 1 minus sine x. If I'm going to multiply that denominator by 1 minus sine x, guess what? We got to multiply that numerator by 1 minus sine x. Now, you could go ahead and distribute, or for the moment, or did you guys go ahead and distribute? Okay, I'll distribute on my next step, okay? Go ahead and distribute there if you want, or we'll distribute on the next step. Okay, but that, yes, you are going to need to multiply them together. Now, we just got a common denominator. What's the plan when you get a common denominator? Put them together, yes? So, my denominator is going to be cosine x times 1 minus sine x. Correct? That's the common denominator I created. Now, my first fraction is just cosine squared x, right? Notice we are subtracting.
So we have put the second numerator in parentheses.
Or we can just go ahead and subtract. In other words, if we're subtracting, it just means we have to distribute the subtraction sign, right?
Yeah.
So, okay, sine x times 1 is, in other words, as you're doing your distributing, I guess what I would maybe even think of it as a negative sine x. That might be the easiest way. Sine x times 1 is just sine x. Because this is a subtraction sign, it's going to be a minus sine x. And then, okay, again, if we're thinking of this as negative sine x out front times the negative sine x in parentheses. Negative sine x times negative sine x is going to be positive what?
Sine squared.
Sine squared x. It's just like the idea of what's x times x is x squared. So what's sine x times sine x? Sine squared x. Okay. Now, I did distribute the denominator. I don't usually distribute the denominator until I find a reason that tells me to distribute the denominator. Maybe I'll need to, maybe I won't. But more often than not, I don't necessarily feel like I have to. Okay, we're still going. I would start examining. Maybe examine your numerator if you want my hint. And, you know, check out those identities.
Cosine squared x plus sine squared x will equal 1. How do we do that?
Okay, what's he referring to?
Pythagorean identity.
Do we have that? I told you guys yesterday when I introduced those. Are we going to use that top identity a lot?
Yeah.
You're going to see that Pythagorean identity. So the identity on your previous page says that sine squared x plus cosine squared x equals 1. Do we have those pieces on top? We do. And I'm even going to rewrite it just for the convincing factor. But yes, because we have those pieces, we can pull those pieces and replace them with a 1. So let me rewrite this. I'm just going to move my sine squared x out front. So it's sine squared x plus cosine squared x, still minus sine x, over cosine x times 1 minus sine x. And I will say, as I write these steps, might you write more steps or less steps than me? Yes, you might. As long as I can follow your steps, I'm good with it. Okay? So you can't just magically jump from the beginning to the end. Okay. Now, if you weren't convinced earlier, are you more convinced now? There's a sine squared plus a cosine squared, which can be replaced with a 1. So on top, I have 1 minus sine x over my denominator, which is cosine x times 1 minus sine x. This was indeed a Pythagorean identity, if you want to write that note to yourself. On top, our entire numerator is 1 minus sine x. On bottom, we have a factor of 1 minus sine x. Can those cancel? We're going to cancel 1 minus sine x with 1 minus sine x. Now, when everything cancels on top, what remains? 1. So at this point, I have 1 over cosine x.
Which is secant x.
1 over cosine x is indeed secant x. And of course, that last step was a reciprocal. Okay. Okay. I'm not sure we're going to make it through all 6 examples, but that's all right. I don't always make it through all 6, so I do what I can do. Because here's the idea. Am I showing you a variety? Am I getting you some ideas? That's the best I can do here is I'm just showing you ideas. What are we going to do on Monday? We're going to spend time talking about your homework. That's the plan for Monday. Because some of these in homework, you're going to be like, okay, yeah, I see that. And others, you're going to be like, I have no clue where to even start. Okay? We're going to spend time talking about them. Okay? I don't think McKenna likes that I'm just stating the obvious here. But I'm just trying to tell you. Okay? I'm not expecting homework to come back next week and you guys be like, oh yeah, piece of cake.
What if I did?
More power to you.
You get all the answers number wrong.
Yeah.
Okay.
That's right.
Okay. I'd like to do D and E.
Yeah.
Okay. Let's try D. Because ideally I'd like to get D and E in. E is a nice E. I love E. Okay, I think you guys.
Pretty easy.
E, I love E. That's a fun one. D, we're gonna have to work. So let's get working so we don't run out of time to get both these in. Okay, tangent x plus cotangent x all over cosecant squared x.
I see cotangent.
You, I don't know. That's
And
I was gonna say change the tangent cotangent to like the sine over cosine stuff. That's a lot.
it is, but it's the way I went. Now, okay, so, and I'm not gonna just change those though. We're gonna change everybody. Yes, it becomes ugly for a moment, but it'll get us somewhere good. Fair enough?
TTP.
Okay, so we are going to change everybody to sine and cosine. Okay. Okay, so what do we know? Tangent is what?
Sine x over cosine x.
Okay. It is sine x over cosine x plus, what do we know about cotangent? Cotangent is cosine x over sine x.
You
Denominator. We're changing everybody to sine and cosine. What do you know about cosecant?
know, it's 1 over sine.
It's the reciprocal of sine. So cosecant squared is 1 over sine squared x?
Wouldn't the top part just equal 1? Or what?
No.
Cancel out.
No.
Can you do any of that?
Nope. Okay. We changed these to sine and cosine. We used our quotient and our reciprocal identities to make that happen. Yes?
Common denominator.
On the top?
Yeah.
And interestingly enough, I was just thinking about that, and that's not the direction I went in my notes, but I might kind of want to go that way.
Alright, well, yeah.
I'm thinking to make sure I know what I want to do here, okay? And it goes with, it's not what I did in my notes, but let's go for it. On top, can we get a common denominator there? On the top two fractions. What's a common denominator if you have cosine and sine? Cosine, sine?
Yeah.
Okay. So, on top, can I go ahead and put it as one fraction, or will that mess you guys up too much?
TBH. I said, I don't know. TBH. To be honest.
Okay, okay. So common denominator on top is going to be what we say, cosine sine, cosine x, sine x, plus another denominator of cosine x, sine x, all going to be over the 1 over sine squared x. If you want to go ahead and put these two fractions together, I'm kind of regretting. I probably should have done that, but it's all right. I'll do it next time. First fraction here. It has a cosine. How do I get to the denominator cosine sine? I multiply by a denominator of sine. Are you guys okay with that? On top, if I multiply the bottom by sine, I'm multiplying the top by sine. You guys are quiet. Are you okay with that? So on top of that fraction, sine x times sine x is going to be
Sine squared x.
sine squared x. Second fraction,
Cosine squared x.
I have sine x. I'm missing the cosine x. So we multiply by cosine x. What we do to the denominator, I do to the numerator. Sine times cosine is the cosine sine. Cosine times cosine,
Cosine squared x.
cosine squared x. Okay. I need to do another rewrite. Those two fractions on top, if you didn't already add them, you need to add them now, right? And as I said, I kind of regret not adding them previously, but so on top, I'm going to have sine squared x plus cosine squared x over my common denominator of cosine x sine x all over the fraction 1 over sine squared x. Okay. Promise. I see so many things getting ready to happen. You see one thing that you can pick out. This will be like our third time doing this today.
Sine squared plus cosine squared, that's 1.
Pythagorean identity, yes? Is it there? Pythagorean identity, folks, it is right there. Sine squared plus cosine squared x is going to become a 1. That is by a Pythagorean identity there, right? Now, I was trying to save my steps here. The other thing I see, fraction divided by fraction, yes? Keep, change, flip. How do we divide fractions, right? Multiply by the reciprocal is what I should say, not for level class, but keep, change, flip is what you guys like to hear. So I'm going to keep my top fraction, which is now 1 over cosine x sine x, yes? You guys good with that? It was divided. I'm going to multiply by the flip. I'm going to reciprocal. And what's my flip? Sine squared x over 1. Okay. So there, if I write KCF, keep, change, flip. I don't know if you need that step written out, but. Okay, guys. What do we do next?
So,
Just think basic algebra here.
one of the sines is going to cancel out on top. And so then you're going to have sine over cosine, which is equal to tangent, and then answer.
Oh.
You guys see it? I was just going for, do we see the fact that there's a sign on top and bottom that can cancel? Do we see that? One sign on bottom cancels with one sign on top. So my squared becomes a 1, right? So then when we multiply across, I have sine x over cosine x. But we have a quotient identity that says sine x over cosine x is tangent x. Okay. Now, is crash course for E? Is that what you're saying?
Yeah.
Okay. E. I'm just going to give it to you straight because I'm that tiny. I see a whole bunch of identities happening here. Anytime I see a negative in the exponent, that is an even odd identity if you look at your front.
Yeah.
Or a negative in the variable. Anytime I see this pi over 2 minus x stuff,
Cofunction.
that's a cofunction. So I'm going to use my cofunction and even odd identities to change all of these out. And then magic will happen. It's really all magic, right? But so tangent of negative x, according to our even odd functions, is what?
Negative.
Negative tan x. And I'm going to put these each in parentheses. According to my even odd functions, cosine of negative x becomes cosine x. According to my even odd functions, sine of negative x becomes negative sine x. According to my even odd functions, secant, not even odd, according to my co-function identities, secant of pi over 2 minus x becomes cosecant x. Now, the magic isn't quite visible yet. All these bad boys need to change to what? Sine and cosine. Everybody changes to sine and cosine. So it's going to stay negative. What does tangent change to?
Negative sine x over cosine x.
And that's using a quotient identity, right? Cosine is already cosine. I'm going to make it a fraction by saying it's cosine x over 1. I'm making a fraction because I know what the last step is. Negative sine x. I'm just going to make it a fraction. It's negative sine x over 1. Cosecant is what?
1 over sine x.
According to our reciprocal identity, it's 1 over sine x. So I just used my quotient identity here, and I used a reciprocal identity here. Okay, guys, basic algebra. A cosine x on bottom cancels with a cosine x on top. A sine x on bottom cancels with a sine x on top. A negative times a negative makes it a positive. What remains?
Just sine of x.
Sine of x. Was that last one okay?
Yeah.
I know I went fast, but I think it's one I can't go fast on. Okay, guys, what I want you to look at for next week. Page 403, 1 through 37 odds. Attempt every problem. Now, are some of them going to be blank attempts? You know, I would at least write the problem down. That's a start. Think through them, see what you can do, bring back your questions Monday, okay? And I expect we're going to spend Monday. That's my plan, questions, okay?